amplifier circuits. An amplifier is a device that enables an input signal to control an output signal. The output signal has some or all of the characteristics of the input signal, but generally is a greater magnitude than the input signal in terms of voltage, current, or power. Gain is the basic function of all amplifiers. Because of this gain, we can expect the output signal to be greater than the input signal. For example, if we have an input signal of 1 volt and an output signal of 10 volts, then the gain factor can be determined by load, band pass filter, load, band pass filter, current, frequency response. Gain equals signal out divided by signal in, gain equals 10V divided by 1V equals 10. Voltage gain is usually used to describe the operation of a small gain amplifier. In this type of an amplifier, the output signal voltage is larger than the input signal voltage. Power gain, on the other hand, is usually used to describe the operation of large signal amplifiers. In the case of power gain amplifiers, the gain is not based on voltage but on watts. A power amplifier is an amplifier in which the output signal power is greater than the input signal power. Most power amplifiers are used as the final stage of amplification, and drive the output device. The output device could be a flight deck or cabin speaker, an indicator, or antenna. Whatever the device, the power to make it work comes from the final stage of amplification. Drivers for autopilot servos are sometimes contained in line replaceable units, called autopilot amplifiers. These units take the low signal commands from the flight guidance system, and amplify the signals to a level usable for driving the servo motors. Classification. The classification of a transistor amplifier circuit is determined by the percentage of the time that the current flows through the output circuit in relation to the input signal. There are 4 classifications of operation: A, B, and C. Each class of operation has a certain use and characteristic. No individual class of amplifiers is considered the best. The best use of an amplifier is a matter of proper selection for the particular operation desired. Class A. In the class operation, the current in the transistor flows for 100%, or 360 degrees of the input signal. Figure 12-238. Class operation is the least efficient class of operation, but provides the best fidelity. Fidelity simply means that the output signal is a good reproduction of the input signal in all respects other than the amplitude, which is amplified. In some cases, there may be some phase shifting between the input signal and the output signal. Typically, the phase difference is 180 degrees. If the output signal is not a good reproduction of the input signal, then the signal is said to be distorted. Distortion is any undesired change to the signal from the input to the output. The efficiency of an amplifier refers to the amount of power delivered to the output compared to the power supplied to the circuit. Every device in the circuit consumes power in order to operate. If the amplifier operates for 360 degrees of input signal, then it is using more power than if it was using only 180 degrees of input signal. The more power consumed by the amplifier, the less there is available for the output signal. Usually the class. Figure 12-237. Band stop filter. 12-116. Plus. VCC. NPN. Output. NPN. Output. Input. VEE. Class A amplifier. Class A amplifier. Figure 12-238. Simplified Class A amplifier circuit. A amplifier is used where efficiency is of little concern, and where fidelity in reproduction is desired. Class A. In the Class A operation, the transistor current flows for more than 50%, but less than 100% of the input signal. Figure 12-239. Unlike the Class A amplifier, the output signal is distorted. A portion of the output circuit appears to be truncated. This is due to the lack of current through the transistor during this point of operation. When the emitter in this case becomes positive enough, the transistor cannot conduct because the base to emitter junction is no longer forward biased. The input signal going positive beyond this point does not produce any further output and the output remains level. The Class A amplifier has a better efficiency and a poorer fidelity than the Class A amplifier. These amplifiers are used when an exact reproduction of the input is not required but both the positive and negative portions of the input signals need to be available on the output. Class B. In Class B operation, the transistor current flows for only 50% of the input signal. Figure 12-240. In this illustration, the base emitter bias does not allow the transistor to conduct whenever the input signal is greater than 0. In this case, only the negative portion of the input signal is reproduced. Unlike the rectifier, the Class B amplifier does not only reproduce half of the input signal, but it also amplifies it. Class B amplifiers. Figure 12-239. Simplified Class A amplifier circuit. Plus. VCC. Dash. NPN. Output. Input. Dash. VEE. Class B amplifier. Figure 12-240. Simplified Class B amplifier circuit. Are twice as efficient as the Class A amplifier, because the amplifying device only uses power for half of the input signal. 12-117. Output. Plus. C1 Q2. VCC. Dash. Input. Q1. Output. NPN. R1 R2. VCC. Input. Dash. VEE. Class C amplifier. Figure 12-241. Simplified Class C amplifier circuit. Class C. In Class C operations, transistor current flows for less than 50% of the input signal. Figure 12-241. This class of operation is the most efficient, because the transistor does not conduct except during a small portion of the input signal. This is the most efficient class of amplifier. The distortion of the Class C amplifier is greater, poor fidelity, than the Class A, IB, and B amplifiers, because a small portion of the input signal is reproduced on the output. Class C amplifiers are used when the output signal is used for only small portions of time. Methods of coupling. Coupling is used to transfer a signal from one stage on an amplifier to another stage. Regardless of whether an amplifier is a single stage, or one in a series of stages, there must be a method for the signal to enter and leave the circuit. Coupling is the process of transferring the energy between circuits. There are a number of ways for making this transfer, and to discuss these methods in detail goes beyond the scope of this text. However, 4 methods are listed below with a brief description of their operation. Direct coupling. Direct coupling is the connection of the output of one stage directly to the input of the next stage. Direct coupling provides a good frequency response, because no frequency-sensitive components, such as capacitors and inductors, are used. Yet this method is not used very often due to the complex power supply requirements and the impedance matching problems. RC-coupled amplifier. Figure 12-242. Simplified RC coupling circuit. RC coupling. RC coupling is the most common method of coupling, and uses a coupling capacitor and signal-developing resistors. Figure 12-242. In this circuit, R1 acts as a load resistor for Q1, and develops the output signal for that stage. The capacitor C1 blocks the DC bias signal, and passes the AC output signal. R2 then becomes the load over which the passes AC signal is developed as an input to the base of Q2. This arrangement allows for the bias voltage of each stage to be blocked, while the AC signal is passed to the next stage. Impedance coupling. Impedance coupling uses a coil as a load for the first stage, but otherwise functions just as an RC coupling. Figure 12-243. This method is similar to the RC coupling method. The difference is that R1 is replaced with inductor L1 as the output load. The amount of signal developed on the output load depends on the inductive reactance of the coil. In order for the inductive reactance to be high, the inductance must be large. The frequency must be high or both. Therefore, load inductors should have relatively large amounts of inductance, and are most effective at high frequencies. Output. C1 Q2. Input. Q1. L1. VCC. Impedance coupled amplifier. Figure 12-243. Simplified impedance coupling circuit. 12-118. Transformer coupling. Transformer coupling uses a transformer to couple the signal from one stage to the next. Figure 12-244. The transformer action of T1 couples the signal from the first stage to the second stage. The primary coil of T1 acts as a load for the output of the first stage, while the secondary coil acts as the developing impedance for the second stage Q2. Transformer coupling is very efficient, and the transformer can aid in impedance matching. Feedback. Feedback occurs when a small portion of the output signal is sent back to the input signal to the amplifier. There are 2 types of feedback in amplifiers. 1. Positive, regenerative. 2. Negative, degenerative. The main difference between these 2 signals is whether the feedback signal adds to the input signal, or if the feedback signal diminishes the input signal. When the feedback is positive, the signal being returned to the input is in phase with the input signal, and thus interferes constructively. Figure 12-245 illustrates this concept applied in the amplified circuit through a block diagram. Notice that the feedback signal is in phase with the input signal, which regenerates the input signal. This results in an output signal with amplitude greater than would have been without the constructive, positive feedback. This type of positive feedback is what causes an audio system to squeal. Figure 12-245 also illustrates with a block diagram how negative or degenerative feedback occurs. In this case, the feedback signal is out of phase with the input signal. This causes destructive interference and degenerates the input signal. The result is a lower amplitude output signal than would have occurred without the feedback. Input, output, positive feedback, input output, output, T1 Q2, input, Q1, VCC, transformer coupled amplifier. Figure 12-244. Simplified transformer coupling circuit. Negative feedback. Figure 12-245. Feedback. Operational amplifiers, op-amp, an operational amplifier, op-amp, is designed to be used with other circuit components and performs either computing functions or filtering. Figure 12-246. Operational amplifiers are usually high-gain amplifiers with the amount of gain governed by the amount of feedback. Operational amplifiers were originally developed for analog computers and used to perform mathematical functions. Today many devices use the operational amplifier for DC amplifiers, AC amplifiers, comparators, oscillators, and filter circuits. The widespread use is due to the fact that the op-amp is a versatile device, small and inexpensive. Built into the integrated chip, the operational amp is used as a basic building block of larger circuits. There are two inputs to the operational amplifier, inverting, dash, and non-inverting, plus, and there is one output. The polarity of a signal applied to the inverting input, dash, is reversed at the output. A signal applied to the non-inverting, plus, input retains its polarity on the output. To be classified as an operational amplifier, the circuit must have certain characteristics. 1. Very high gain. 2. Very high input impedance. 3. Very high output impedance. This type of a circuit can be made up of discrete components, such as resistors and transistors. However, the most common form of an operational amplifier is found in the integrated 12-119. 4. 5. 1. 2. 3. 4. 1. 2. 3. 4. Plus VCC. Dash. Inputs. Output. Plus. VEE. Power supply requirements. Dash. Inputs output. Plus. Input/output requirements. Plus VCC. Dash. Inputs output. Plus. VEE. Feedback. Figure 12-246. Schematic symbol for the operational amplifier. Circuit. This integrated circuit or chip contains the various stages of the operational amplifier, and can be treated as if it were a single stage. Applications. The number of applications for op-amps is too numerous to detail in this text. However, the technician occasionally comes across these devices in modern aircraft, and should be able to recognize their general purpose in a circuit. Some of the basic applications are: 1. Go/no-go detectors. 2. Square wave circuits. 3. Non-inverting amplifier. Inverting amplifier half-wave rectifier. Magnetic amplifiers. Magnetic amplifiers do not amplify magnetism, but use electromagnetism to amplify a signal. Essentially, the magnetic amplifier is a power amplifier with a very limited frequency response. The frequency range most commonly associated with the magnetic amplifier is 100 Hz and less, which places it in the audio range. As a technical point, the magnetic amplifier is a low-frequency amplifier. Advantages of the magnetic amplifier are: very high efficiency, on the order of approximately 90%. High reliability. Very rugged, able to withstand vibrations, moisture, and overloads. No warm-up time. Some of the disadvantages of the magnetic amplifier are: incapacity to handle low-voltage signals, not usable in high-frequency applications, time delay associated with magnetic effects, poor fidelity. The basic operating principles of the magnetic amplifier are fairly simple. Keep in mind that all amplifiers are current control devices. In this particular case, power that is delivered to the load is controlled by a variable inductance. If an AC voltage is applied to the primary winding of an iron core transformer, the iron core is magnetized and demagnetized at the same frequency as that of the applied voltage. This, in turn, induces a voltage in the transformer's secondary winding. The output voltage across the terminals of the secondary depends on the relationship of the number of turns in the primary and the secondary of the transformer. The iron core of the transformer has a saturation point after which the application of a greater magnetic force produces no change in the intensity of magnetization. Hence, there is no change in transformer output, even if the input is greatly increased. The magnetic amplifier circuit in Figure 12-247 is used to explain how a simple magnetic amplifier functions. 1. Assume that there is 1 ampere of current in coil, which has 10 turns of wire. If coil B has 10 turns of 12-120. B. AC input, AC output. C. DC. Figure 12-247. Magnetic amplifier circuit. Wire. An output of 1 ampere is obtained if coil B is properly loaded. 2. By applying direct current to coil C, the core of the magnetic amplifier coil can be further magnetized. Assume that coil C has the proper number of turns and, upon the application of 30 milliamperes, that the core is magnetized to the point where 1 ampere on coil A results in only 0.24 ampere output from coil B. 3. By making the DC input to coil C a continuous variable from 0 to 30 milliamperes, and by maintaining an input of 1 ampere on coil A, it is possible to control the output of coil B to any point between 0.24 ampere and 1 ampere in this example. The term amplifier is used for this arrangement because, by use of a few milliamperes, control of an output of 1 or more amperes is obtained. Saturable core reactor. The same procedure can be used with the circuit shown in figure 12-248. A saturable core reactor is a magnetic core coil whose reactance is controlled by changing the permeability of the core. Varying the unidirectional flux controls the permeability of the core. By controlling the extent of magnetization of the iron ring, it is possible to control the amount of current flowing to the load. Since the amount of magnetization controls the impedance of the AC input winding. This type of magnetic amplifier is called a simple saturable reactor circuit. Adding a rectifier to such a circuit would remove half the cycle of the AC input and permit DC to flow to the load. The amount of DC flowing in the load circuit is controlled by a DC control winding, sometimes referred to as bias. This type of magnetic amplifier is referred to as being self-saturating. To use the full AC input power, a circuit such as that shown in figure 12-249 may be used. This circuit uses a full-wave bridge rectifier. The load receives a controlled DC by using the full AC input. This type of circuit is known as a self-saturating, full-wave magnetic amplifier. In figure 12-250, it is assumed that the DC control winding is supplied by a variable source, such as a sensing circuit. To control such a source and use its variations to control the AC output, it is necessary to include another DC winding that has a constant value. This winding, referred to as the reference winding, magnetizes the magnetic core in one direction. The DC control winding, acting in opposition to the reference winding, either increases, degenerative, or decreases, regenerative, the magnetization of the core to change the amount of current flowing through the load. This is essentially a basic preamplifier. DC, load, load, DC, AC input, AC, figure 12-248. Saturable core reactor circuit, figure 12-249. Self-saturating, full-wave magnetic amplifier, 12-121. DC control, load, DC ref, AC, figure 12-250. Basic preamplifier circuit, logic circuits. Logic is considered the science of reasoning, the development of a reasonable conclusion based on known information. Human reasoning tells us that certain propositions are true, if certain conditions or premises are true. An annunciator being lit in the master warning panel is an example of a proposition, which is either true or false. For example, predetermined and designed conditions must be met in order for an annunciator in a master warning panel to be lit. A low hydraulic press annunciator may have a simple set of conditions that cause it to be illuminated. If the conditions are met, such as a hydraulic reservoir that is low on fluid causing the line press to be low, then the logic is true, and the annunciator lights. Several propositions, when combined, form a logical function. In the example above, the low hydraulic press annunciator is on if the lead is not burned out and the hydraulic press is low, or if the lead is not burned out and the annunciator test is being asserted. This section on logic circuits only serves as an introduction to the basic concepts. The technician encounters many situations or problems in everyday life that can be expressed in some form of a logical function. Many problems and situations can be condensed down to simple yes/no or true/false statements that, if logically ordered, can filter a problem down to a reasonable answer. The digital logic circuits are well suited for this task, and have been employed in today's integrated circuits found in virtually all of the devices that we take for granted in modern aircraft. These logical circuits are used to carry out the logical functions for such things as navigation and communications. There are several fundamental elements that form the building blocks of the complex digital systems found in line replaceable units, LRUs, and avionics card cages. The following is a very basic outline of what those elements are and what logic conditions they process. It is far beyond the scope of this text to cover digital logic systems due to the vast body of knowledge that it represents. However, this serves as an introduction and, in some limited cases, is useful in reading system block diagrams that use logic symbols to aid the technician in understanding how a given circuit operates. Logic polarity. Electrical pulses can represent two logic conditions, and any two differing voltages can be used for this purpose. For example, a positive voltage pulse could represent a true, or one condition, and a negative voltage pulse could then represent a false, or zero logic condition. The condition in which the voltage changes to represent a true, or one logic is known as the logic polarity. Logic circuits are usually divided into two broad classes, positive polarity and negative polarity. The voltage levels used and a statement indicating the use of positive or negative logic is usually specified in the logic diagrams provided by the original equipment manufacturers. Ohms. Positive. When a signal that activates a circuit to a 1, true or high condition, has an electrical level that is relatively more positive than the other 0 or false condition, then the logic polarity is said to be positive. An example would be, active state, 1 or true equals plus 5 volts direct current, VDC, 0 or false equals minus 5 VDC. Negative. When the signal that activates a circuit to a 1, true or high condition, has an electrical level that is relatively more negative than the other 0 or false condition, then the logic polarity is said to be negative. An example would be, active state, 1 or true equals 0 VDC, 0 or false equals plus 5 VDC. Pulse structure. Figure 12-251 illustrates the positive and negative pulse in an idealized form. In both forms, the pulse is composed of two edges, one being the leading edge, and the other the trailing edge. In the case of the positive pulse logic, the positive transition from a lower state to a higher state is the leading edge, and the trailing edge is the opposite. In the case of the negative logic pulse, the negative transition from a higher state to a lower state is the leading edge, while the rise from the lower state back to the higher state is the trailing edge. Figure 12-251 is considered an ideal pulse, because the rise and fall times are instantaneous. In reality, these changes take time, although in actual practice, the rise and fall can. 12-122. High, leading edge. Low, trailing edge. Positive logic pulse. High, leading edge. Low, trailing edge. Negative logic pulse. Figure 12-251. Positive and negative pulse in an idealized form. Be assumed as instantaneous. Figure 12-252 shows an ideal pulse and its characteristics. The time required for a pulse to go from a low state to a high state is called the rise time, and the time required for the pulse to return to 0 is called the fall time. It is common practice to measure the rise and fall time between 10% amplitude and 90% amplitude. The reason for taking the measurements in these points is due to the nonlinear shape of the pulse in the first 10% and final 90% of the rise and fall amplitudes. The pulse width is defined as the duration of the pulse. To be more specific, it is the time between the 50% amplitude point on both the pulse rise and fall. Basic logic circuits. Boolean logic is a symbolic system used in representing the truth value of statements. It is employed in the binary system used by digital computers primarily because the only truth values, true and false, can be represented by the binary digits 1 and 0. A circuit in computer memory can be open or closed, depending on the value assigned to it. The fundamental operations of Boolean logic, often called Boolean operators, are and, or, and, not. Combinations of these make up 13 other Boolean operators. 6 of these operators are discussed. The inverter logic. The inverter circuit performs a basic logic function called inversion. The purpose of the inverter is to convert one logic state into the opposite state. In terms of a binary digit, this would be like converting a 1 to a 0 or a 0 to a 1. When no high voltage is applied to the inverter input, low voltage is the output. When a low voltage is applied to the input, a high voltage is on the output. This operation can be put into what is known as a logic or truth table. The standard logic symbol is shown in figure 12-253. Figure 12-254 shows the possible logic states for this gate. This is the common symbol for an amplifier with a small circle on the output. This type of logic can also be considered a NOT gate. The AND gate. The AND gate is made up of 2 or more inputs and a single output. The logic symbol is shown in figure 12-255. Inputs are on the left and the output is on the right in each of them. Input equals 1. High, output equals 0. Low, figure 12-253. Standard logic symbol. Input output. High low. Figure 12-254. Possible logic states. Low high. X. B. X. Pulse amplitude. 10 volts. 90% 9V, 50% 5V, pulse width, 10% 1V, fall time, rise time, X, pulse characteristic from a date of use, figure 12-252, non-ideal pulse and its characteristics, ABC, A, B, C, D, figure 12-255, and gate logic symbol, 12-123, a B, plus, dash, F equals a plus B, B, OR gate input slash output, a BF 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1, a B, plus, dash, figure 12-256. Simplified diagram of the AND logic. Depictions. Gates with 2, 3, and 4 inputs are shown. However, any number of inputs can be used in the AND logic as long as the number is greater than 1. The operation of the AND gate is such that the output is high only when all of the inputs are high. If any of the inputs are low, the output is also low. Therefore, the basic purpose of an AND gate is to determine when certain conditions have been met at the same time. A high level on all inputs produces a high level on the output. Figure 12-256 shows a simplified diagram of the AND logic with 2 switches and a light bulb. Notice that both switches need to be closed in order for the light bulb to turn on. Any other combination of switch positions is an open circuit and the light does not turn on. An example of it. Figure 12-258. OR gate. Logic could possibly be engaged logic found in an autopilot. In this case, the autopilot would not be allowed to be engaged unless certain conditions are first met. Such conditions could be, vertical gyro is valid and directional gyro is valid and all autopilot control knobs are independent and servo circuits are operational. Only when these conditions are met does the autopilot engage. Figure 12-257, the OR gate. The OR gate has 2 or more inputs and 1 output, and is normally represented by the standard logic symbol and truth table. Figure 12-258, note that the OR gate can have any number of inputs as long as it is greater than 1. The operation of the OR gate is such that a high on any one of the inputs produces a high on the output. The only time that a low is produced on the output is if there are no high levels on any input. Figure 12-259 is a simplified circuit that illustrates the OR logic. The example used is a door and safe annunciator. Let's say in this case that the plane has 1 cabin door and a baggage door. In order for the annunciator light on the master warning panel to extinguish both doors. Rs plus 28 VDC. Pitch servo valley plus 28. Roll servo valley plus 28. Yaw damper valley plus 28. Trim servo valley plus 28. Rs plus 28 VDC. Attitude slash heading reference system. Rs. Attitude valley plus 28. Heading valley plus 28. Autopilot controller. Pitch wheel centered. Turn knob centered. Plus 28 VDC plus 28 VDC plus 28 VDC plus 28 VDC. Plus 28 VDC plus 28 VDC plus 28 VDC plus 28 VDC. Plus 28 VDC. Autopilot computer. Engage circuit. When all input circuits are valid, then the /P can be engaged. A /P controller plus 28 VDC. Autopilot engage logic. Figure 12-257. And logic of system found in the aircraft wiring diagrams. 12-124. Cabin door secured. Door worn. Plus 28 VDC baggage door secured. Light off. Door unsafe. 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 0, 1. Cabin door not secured. Door worn. Plus 28 VDC baggage door secured. Light on. Door unsafe. And gate input / output. Figure 12-259. Simplified circuit that illustrates OR logic. Must be closed and locked. If any one of the doors is not secured properly, the baggage door or the cabin door, then the door unsafe annunciator illuminates. In this case, 2 switches are in parallel with each other. If either one of the 2 switches is closed, the light bulb lights up. The lamp is off only when both switches are open. The NAND gate. The term NAND is a combination of the NOT AND gate and indicates AND function with an inverted output. A standard logic symbol for a 2-input NAND gate is shown in figure 12-260. Notice that an equivalent AND gate with an inverter is also shown. The logical operation of the NAND gate is such that a low output occurs only if all inputs are high. If any of the inputs are low, the output is high. An example of a 2-input NAND gate and its corresponding truth table are shown in figure 12-261. The NOR gate. The term NOR is a combination of the NOT and OR and indicates an OR function with an inverted output. The A 0 1 0 1 B 0 0 1 1 NAND gate truth table F 1 1 1 0. Figure 12-261. 2-input NAND gate and corresponding truth table. Standard logic symbol for a 2-input NOR gate is shown in figure 12-263. Notice that an equivalent AND gate with an inverter is also shown. The logical operation of the NOR gate is such that a low output happens when any of its inputs are high. Only when all of its inputs are low is the output high. The logic of this gate produces resultant outputs that are the opposite of the OR gate. In the NOR gate, the low output is the active output level. Figure 12-263 illustrates the logical operation of a 2-input NOR gate for all of its possible combinations and the truth table. Exclusive OR gate. The exclusive OR gate is a modified OR gate that produces a 1 output when only one of the inputs is a 1. The abbreviation often used is XOR. It is different from the standard OR gate in that when both inputs are a 1, then the output remains at a 0. The standard symbol and truth table for the XOR gate are shown in figure 12-264. FB NAND gate. F equals A plus BB. OR gate input / output. 1 0 FB 0 1 FB. Equivalent circuit NAND gate input / output. A 0 1 0 1 B 0 0 1 1. Truth table F 0 1 1 1. Figure 12-262. Standard logic symbol for 2 inputs OR gate. Figure 12-260. Standard logic symbol for 2-input NAND gate. 12-125. 0 1 0 0 0 1 1 0 0 1 0 1 A 0 0 1 1. NOR gate input / output. B 0 1 0 1. NOR gate truth table F 1 0 0 0. Figure 12-263. Logical operation of 2-input NOR gate and truth table. Exclusive NOR gate. The exclusive NOR XNOR gate is nothing more than an XOR gate with an inverted output. It produces a 1 output when all inputs are 1 second, and also when all inputs are 0 seconds. The standard symbol is shown in figure 12-265. The integrated circuit. All of the logic functions so far discussed plus many other components are available in some form of an integrated circuit. The digital systems found in today's aircraft owe their existence to a large extent to the design of the integrated circuit, IC. In most cases, the IC has an advantage over the use of discrete components in that they are smaller, consume less power, are very reliable, and are inexpensive. The most noticeable characteristic of the IC is its size, and in comparison to the discrete semiconductor component, can easily be on the order of thousands of times smaller. Figure 12-266. T0, T1, T2, T3, T4, T4. T0, T1, T2, T3, T4, T5. 0. A. 1. 0, 0. 1. F. 0. F. 1. 1. 0, 0. B. 0. B. 0, 0. 1. 1. A. 0. 0. 1. 1. B. 0. 1. 0. 1. F. 0. 1. 1. 0. XOR gate input / output truth table. Figure 12-264. Standard symbol and truth table for XOR gate. T0, T1, T2, T3, T4. T0, T1, T2, T3, T4. 0. A. 1. 0. 1. F equals A plus B. 0. F. 0. 0. B. 1. 0. B. 0. 1. 1. A. 0. 0. 1. 1. B. 0. 1. 0. 1. F. 1. 0. 0. 1. XNOR gate input / output truth table. Figure 12-265. Standard symbol for X NOR gate. 12-126. 16, 15, 14, 13, 12, 11, 10, 9. 4Y, 4A, 4B, GND, 3A, 3B, 3Y. 14, 13, 12, 11, 10, 9, 8. 0.280 max. 1, 2, 3, 4, 5, 6, 7, 8. 0.785 max. 0.200 max. Typical integrated logic circuit. Figure 12-266. Integrated circuit. 1, 2, 3, 4, 5, 6, 7. 1Y, 1A, 1B, VCC, 2A, 2B, 2Y. A monolithic integrated circuit is an electronic circuit that is constructed entirely on a single chip or wafer of semiconductor material. All of the discrete components, such as resistors, transistors, diodes, and capacitors, can be constructed on these small pieces of semiconductor material, and are an integral part of the chip. There are a number of levels of integration. Those levels are small-scale integration, medium-scale integration, large-scale integration, and microprocessors. The small-scale integration is considered the least complex design of the digital ICs. These ICs contain the basic components, such as the AND, OR, NOT, NOR and NAND gates. Figure 12-267. The medium-scale integration can contain the same components as found in the small-scale design, but in larger numbers ranging from 12 to 100. The medium-scale designs are house circuits that are more complex, such as encoders, decoders, registers, counters, multiplexers, smaller memories, and arithmetic circuits. Figure 12-268. The large-scale integrated circuits contain even more logic gates, larger memories than the medium-scale circuits, and in some cases microprocessors. Microprocessors. The microprocessor is a device that can be programmed to perform arithmetic and logical operations and other functions in a pre-ordered sequence. The microprocessor is usually used as the central processing unit, CPU, in today's computer systems when it is connected to other components, such as memory chips and input/output circuits. The basic arrangement and design of the circuits residing in the microprocessor is called the architecture. DC generators. Theory of operation. In the study of alternating current, basic generator principles were introduced to explain the generation of an AC voltage by a coil rotating in a magnetic field. Since this is the basis, quad-exclusive OR circuit. Input-output A, B, Y, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0. Figure 12-267. Small-scale integration schematic form. 1Q, 2Q, 2Q enable GND, 3Q, 3Q, 4Q. 16, 15, 14, 13, 12, 11, 10, 9. QD, GQ, DQ, G, Q, QD, GQ, DQ, G, Q. 1, 2, 3, 4, 5, 6, 7, 8. 1Q, 1D2D enable VCC, 3D4, D4Q. D register. Figure 12-268. Medium-scale integration schematic form. For all generator operation, it is necessary to review the principles of generation of electrical energy. When lines of magnetic force are cut by a conductor passing through them, voltage is induced in the conductor. The 12-127. Strength of the induced voltage is dependent upon the speed of the conductor and the strength of the magnetic field. If the ends of the conductor are connected to form a complete circuit, a current is induced in the conductor. The conductor and the magnetic field make up an elementary generator. This simple generator is illustrated in figure 12-269, together with the components of an external generator circuit which collect and use the energy produced by the simple generator. The loop of wire, figure 12-269A and B, is arranged to rotate in a magnetic field. When the plane of the loop of wire is parallel to the magnetic lines of force, the voltage induced in the loop causes a current to flow in the direction indicated by the arrows in figure 12-269. The voltage induced at this position is maximum, since the wires are cutting the lines of force at right angles, thus cutting more lines of force per second than in any other position relative to the magnetic field. As the loop approaches the vertical position shown in figure 12-270, the induced voltage decreases because both sides of the loop, A and B, are approximately parallel to the lines of force and the rate of cutting is reduced. When the loop is vertical, no lines of force are cut since the wires are momentarily traveling parallel to the magnetic lines of force, and there is no induced voltage. As the rotation of the loop continues, the number of lines of force cut increases until the loop has rotated an additional 90 degrees to a horizontal plane. As shown in figure 12-271, the number of lines of force cut in the induced voltage once again are maximum. The direction of cutting, however, is in the opposite direction to that occurring in figures 12-269 and 12-270, so the direction, polarity, of the induced voltage is reversed. As rotation of the loop continues, the number of lines of force having been cut again decreases, and the induced voltage becomes zero at the position shown in figure 12-272, since the wires A and B are again parallel to the magnetic lines of force A, SN, B, figure 12-270, inducing minimum voltage in an elementary generator. A, SN, B, figure 12-271, inducing maximum voltage in the opposite direction. Armature, pole piece, A, B, SN, slip ring, B, SN, A, load, brush, figure 12-272, inducing a minimum voltage in the opposite direction. Figure 12-269, inducing maximum voltage in an elementary generator. 12-128, voltage plus voltage, maximum 360 degrees 1 cycle, 0 degrees, minimum 180 degrees, 90 degrees 270 degrees 360 degrees, maximum. SN, figure 12-273, output of an elementary generator. If the voltage induced throughout the entire 360 degrees of rotation is plotted, the curve shown in figure 12-273 results. This voltage is called an alternating voltage because of its reversal from positive to negative value, first in one direction and then in the other. To use the voltage generated in the loop for producing a current flow in an external circuit, some means must be provided to connect the loop of wire in series with the external circuit. Such an electrical connection can be effected by opening the loop of wire and connecting its two ends to two metal rings, called slip rings, against which two metal or carbon brushes ride. The brushes are connected to the external circuit by replacing the slip rings of the basic AC generator with two half cylinders. Called a commutator, a basic DC generator is obtained. Figure 12-274. In this illustration, the black side of the coil is connected to the black segment, and the white side of the coil to the white segment. The segments are insulated from each other. The two stationary brushes are placed on opposite sides of the commutator, and are so mounted that each brush contacts each segment of the commutator as the latter revolves simultaneously with the loop. The rotating parts of a DC generator, coil and commutator, are called an armature. Figure 12-274. Basic DC generator. The generation of an EMF by the loop rotating in the magnetic field is the same for both AC and DC generators, but the action of the commutator produces a DC voltage. Generation of a DC voltage. Figure 12-275 illustrates in an elementary, step-by-step manner, how a DC voltage is generated. This is accomplished by showing a single wire loop rotating through a series of positions within a magnetic field. Position A. The loop starts in position A and is rotating clockwise. However, no lines of force are cut by the coil sides, which means that no EMF is generated. The black brush is shown coming into contact with the black segment of the commutator, and the white brush is just coming into contact with the white segment. Of ACDE. Induced EMF. 1 revolution. Figure 12-275. Operation of a basic DC generator. 12-129. Position B. In position B, the flux is now being cut at a maximum rate, which means that the induced EMF is maximum. At this time, the black brush is contacting the black segment, and the white brush is contacting the white segment. The deflection of the meter is toward the right, indicating the polarity of the output voltage. Position C. At position C, the loop has completed 180 degrees of rotation. Like position A, no flux lines are being cut and the output voltage is 0. The important condition to observe at position C is the action of the segments and brushes. The black brush at the 180 degrees angle is contacting both black and white segments on one side of the commutator, and the white brush is contacting both segments on the other side of the commutator. After the loop rotates slightly past the 180 degrees point, the black brush is contacting only the white segment, and the white brush is contacting only the black segment. Because of this switching of commutator elements, the black brush is always in contact with the coil side moving downward, and the white brush is always in contact with the coil side moving upward. though the current actually reverses its direction in the loop in exactly the same way as in the AC generator. Commutator action causes the current to flow always in the same direction through the external circuit or meter. Position D. At position D, commutator action reverses the current in the external circuit, and the second half cycle has the same waveform as the first half cycle. The process of commutation is sometimes called rectification, since rectification is the converting of AC voltage to DC voltage. The neutral plane. At the instant that each brush is contacting two segments on the commutator, figure 12-275A, C, and D, a direct short circuit is produced. If an EMF were generated in the loop at this time, a high current would flow in the circuit, causing an arc and thus damaging the commutator. For this reason, the brushes must be placed in the exact position, where the short occurs when the generated EMF is 0. This position is called the neutral plane. If the brushes are installed properly, no sparking occurs between the brushes and the commutator. Sparking is an indication of improper brush placement, which is the main cause of improper commutation. The voltage generated by the basic DC generator in figure 12-275 varies from 0 to its maximum value twice for each revolution of the loop. This variation of DC voltage is called ripple, and may be reduced by using more loops, or coils, as shown in figure 12-276A. As the number of loops is increased, the variation between maximum and minimum values of voltage is reduced, figure 12-276B, and the output voltage of the generator approaches a steady DC value. In figure 12-276A, the number of commutator segments is increased in direct proportion to the number of loops. That is, there are 2 segments for 1 loop, 4 segments for 2 loops, and 8 segments for 4 loops. The voltage induced in a single turn loop is small. Increasing the number of loops does not increase the maximum value of generated voltage, but increasing the number of turns in each loop increases this value. Within narrow limits, the output voltage of a DC generator is determined by the product of the number of turns per loop, the total flux per pair of poles in the machine, and the speed of rotation of the armature. An AC generator, or alternator, and a DC generator are identical as far as the method of generating voltage in the rotating loop is concerned. However, if the current is taken from the loop by slip rings, it is an alternating current, and the generator is called an AC generator, or alternator. If the current is collected by a commutator, it is direct current, and the generator is called a DC generator. SN. A. ABCDE. Induced EMF. 0 and 1/4 1/2 3/4 1. Revolutions. B. Figure 12-276. Increasing the number of coils reduces the ripple in the voltage. 12-130. Construction features of DC generators. Generators used on aircraft may differ somewhat in design, since various manufacturers make them. All, however, are of the same general construction and operate similarly. The major parts, or assemblies, of a DC generator are a field frame, or yoke, a rotating armature, and a brush assembly. The parts of a typical aircraft generator are shown in figure 12-277. Field frame. The field frame is also called the yoke, which is the foundation or frame for the generator. The frame has 2 functions. It completes the magnetic circuit between the poles and acts as a mechanical support for the other parts of the generator. In figure 12-278A, the frame for a 2-pole generator is shown in a cross-sectional view. A 4-pole generator frame is shown in figure 12-278B. In small generators, the frame is made of one piece of iron. But in larger generators, it is usually made up of 2 parts bolted together. The frame has high magnetic properties and, together with the pole pieces, forms the major part of the magnetic circuit. The field poles are bolted to the inside of the frame, and form the core on which the field coil windings are mounted. Figure 12-278. The poles are usually laminated to reduce eddy current losses, and serve the same purpose as the iron core of an electromagnet. That is, they concentrate the lines of force produced by the field coils. The entire frame, including field poles, is made from high-quality magnetic iron or sheet steel. A practical DC generator uses electromagnets instead of permanent magnets. To produce a magnetic field of the necessary strength with permanent magnets would greatly increase the physical size of the generator. The field coils are made up of many turns of insulated wire, and are usually wound on a form that fits over the iron core of the pole to which it is securely fastened. Figure 12-279. The exciting current, which is used to produce the magnetic field, and which flows through the field coils, is obtained from an external source or from the generated DC of the machine. No electrical connection exists between the windings of the field coils and the pole pieces. Most field coils are connected so that the poles show alternate polarity. Since there is always one north pole for each south pole, There must always be an even number of poles in any generator. Note that the pole piece is in figure 12-278 project from the frame. Because air offers a great amount of reluctance to the magnetic field, this design reduces the length of the air gap between the poles and the rotating armature and increases connector legs, air scoop, brush connector bars, commutator, steel ring, sealed ball bearings, field frame drive end frame, drive shaft, commutator end frame, brush end holder, pole shoe screw field winding, field frame, armature drive end, figure 12-277, typical 24-volt aircraft generator, 12-131, flux, frame, NS, pole, field winding, A, figure 12-279, a field coil removed from a field pole, flux, frame, S, and N, pole, S, field winding, B, figure 12-278, a 2-pole and a 4-pole frame assembly, the efficiency of the generator. When the pole pieces are made to project, they are called salient poles. Figure 12-278, armature. The armature assembly of a generator consists of many armature coils wound on an iron core, a commutator, and associated mechanical parts. These additional loops of wire are actually called windings, and are evenly spaced around the armature, so that the distance between each winding is the same. Mounted on a shaft, it rotates through the magnetic field produced by the field coils. The core of the armature acts as an iron conductor in the magnetic field and, for this reason, is laminated to prevent the circulation of eddy currents. Gram ring armature. There are two general kinds of armatures, the ring and the drum. Figure 12-280 shows a ring-type armature made up of an iron core, an 8-section winding, and an 8-segment commutator. The disadvantage of this arrangement is that the windings, located on the inner side of the iron ring, cut few lines of flux. As a result, they have very little voltage induced in them. For this reason, the gram ring armature is not widely used. Drum-type armature. A drum-type armature is shown in figure 12-281. The armature core is in the shape of a drum, and has slots cut into it where the armature windings are placed. The advantage is that each winding completely surrounds the core, so that the entire length of the conductor cuts through the magnetic flux. The total induced voltage in this arrangement is far greater than that of the gram ring-type armature. Drum-type armatures are usually constructed in one of two methods, lap winding and the wave winding, each method having its own advantage. Lap windings are used in generators that are designed for high current. The windings are connected in parallel paths, and for this reason require several brushes. The wave winding is used in generators that NS, figure 12-280, an 8-section, ring-type armature, 12-132. Commutator slots. Shaft coils, figure 12-281, a drum-type armature, are designed for high-voltage outputs. The two ends of each coil are connected to commutator segments separated by the distance between poles. This results in a series arrangement of the coils, and is additive of all the induced voltages. Commutators. Figure 12-282 shows a cross-sectional view of a typical commutator. The commutator is located at the end of an armature, and consists of wedge-shaped segments of hard-drawn copper, insulated from each other by thin sheets of mica. The segments are held in place by steel V-rings or clamping flanges fitted with bolts. Rings of mica insulate the segments from the flanges. The raised portion of each segment is called a riser, and the leads from the armature coils are soldered to the risers. When the segments have no risers, the leads are soldered to short slits in the ends of the segments. The brush is right on the surface of the commutator, forming the electrical contact between the armature coils and the external circuit. A flexible, braided copper conductor, commonly called a pigtail, connects each brush to the external circuit. The brushes, usually made of high-grade carbon and held in place by brush holders insulated from the frame, are free to slide up and down in their holders in order to follow any irregularities in the surface of the commutator. The brushes are usually adjustable, so that the pressure of the brushes on the commutator can be varied and the position of the brushes with respect to the segments can be adjusted. The constant making and breaking of connections to the coils in which a voltage is being induced necessitates the use of material for brushes, which has a definite contact resistance. Also, this material must be such that the friction between the commutator and the brush is low, to prevent excessive wear. For these reasons, the material commonly used for brushes is high-grade carbon. The carbon must be soft enough to prevent undue wear of the commutator, and yet hard enough to provide reasonable brush life. Since the contact resistance of carbon is fairly high, the brush must be quite large to provide a large area of contact. The commutator surface is highly polished to reduce friction as much as possible. Oil or grease must never be used on a commutator, and extreme care must be used when cleaning it to avoid marring or scratching the surface. Commutator bars. Mica insulation between bars. Tightening nut. Iron ring. Mica veer-ing. Front veer-ing. Commutator bar. Mica. Iron shell. Slots back veering with mica inner and outer rings for insulation. Figure 12-282. Commutator with portion removed to show construction. 12-133. Armature reaction. Current flowing through the armature sets up electromagnetic fields in the windings. These new fields tend to distort or bend the magnetic flux between the poles of the generator from a straight line path. Since armature current increases with load, the distortion becomes greater with an increase in load. This distortion of the magnetic field is called armature reaction. Figure 12-283. Armature windings of a generator are spaced so that, during rotation of the armature, there are certain positions when the brushes contact two adjacent segments, thereby shorting the armature windings to these segments. When the magnetic field is not distorted, there is usually no voltage being induced in the shorted windings, and therefore no harmful results occur from the shorting of the windings. However, when the field is distorted, a voltage is induced in these shorted windings, and sparking takes place between the rotation A, neutral plane, plus, NS, A, B, field excited, armature unexcited, rotation, S, B, plus, N, armature excited, field unexcited, A, NS, rotation, B, C, both field and armature excited. Figure 12-283. Armature reaction. Brushes and the commutator segments. Consequently, the commutator becomes pitted, the wear on the brushes becomes excessive, and the output of the generator is reduced. To correct this condition, the brushes are set so that the plane of the coils, which are shorted by the brushes, is perpendicular to the distorted magnetic field, which is accomplished by moving the brushes forward in the direction of rotation. This operation is called shifting the brushes to the neutral plane or plane of commutation. The neutral plane is the position where the plane of the two opposite coils is perpendicular to the magnetic field in the generator. On a few generators, the brushes can be shifted manually ahead of the normal neutral plane to the neutral plane caused by field distortion. On non-adjustable brush generators, the manufacturer sets the brushes for minimum sparking. Compensating windings or interpoles may be used to counteract some of the effects of field distortion, since shifting the brushes is inconvenient and unsatisfactory, especially when the speed and load of the generator are changing constantly. Compensating windings. The compensating windings consist of a series of coils embedded in slots in the pole faces. These coils are also connected in series with the armature. Consequently, this series connection with the armature produces a magnetic field in the compensating windings that varies directly with the armature current. The compensating windings are wound in such a manner that the magnetic field produced by them counteracts the magnetic field produced by the armature. As a result, the neutral plane remains stationary in any magnitude of armature current. With this design, once the brushes are set correctly, they do not need to be moved again. Figure 12-284 illustrates how the windings are set into the pole faces. Interpoles. An interpole is a pole placed between the main poles of a generator. An example of interpole placement is shown in Figure 12-284b. This is a simple two-pole generator with two interpoles. An interpole has the same polarity as the next main pole in the direction of rotation. The magnetic flux produced by an interpole causes the current in the armature to change direction as an armature winding passes under it. This cancels the electromagnetic fields about the armature windings. The magnetic strength of the interpoles varies with the load on the generator. And since field distortion varies with the load, the magnetic field of the interpoles counteracts the effects of the field set up around the armature windings and minimizes field distortion. Thus, the interpole tends to keep the neutral plane in the same position for all loads on. 12-134. Armature windings. Compensating windings. Compensating windings. A. Field rheostat. Plus. Dash. Plus. Dash. SN. Plus. Load. Generator. A compensating. B. Interpole windings. Main field windings. S. Dash. NS. Plus. N. Field coils. to load arm. Main field windings. External load. Interpole windings. Generator. P interpole. Figure 12-284. Simple two-pole generator with two interpoles. The generator. Therefore, field distortion is reduced by the interpoles, and the efficiency, output, and service life of the brushes are improved. Types of DC generators. There are three types of DC generators: series wound, shunt wound, and shunt series or compound wound. The difference in type depends on the relationship of the field winding to the external circuit. Series wound DC generators. The field winding of a series generator is connected in series with the external circuit called the load. Figure 12-285. The field coils are composed of a few turns of large wire. The magnetic field strength depends more on the current flow rather than the number of turns in the coil. Series generators have very poor voltage regulation under changing load, since the greater the current through the field coils to the external circuit. Figure 12-285. Diagram and schematic of a series wound generator. Greater the induced EMF, and the greater the terminal or output voltage. Therefore, when the load is increased, the voltage increases. Likewise, when the load is decreased, the voltage decreases. The output voltage of a series wound generator may be controlled by a rheostat in parallel with the field windings. Figure 12-285A. Since the series wound generator has such poor regulation, it is never employed as an airplane generator. Generators in airplanes have field windings, which are connected either in shunt or in compound. Shunt wound DC generators. A generator having a field winding connected in parallel with the external circuit is called a shunt generator. Figure 12-286A and B. The field coils of a shunt generator contain many turns of small wire. The magnetic strength is derived from the large number of turns rather than the current strength through the coils. If a constant voltage is desired, the shunt wound generator is not suitable for rapidly fluctuating loads. Any increase in load causes a decrease in the terminal or output voltage, and any decrease in load causes an increase in terminal voltage. Since the armature and the load are connected in series, all current flowing in the external circuit passes through the armature winding. Because of the resistance in the armature winding, there is a voltage drop. IR drop equals current times resistance. As the load increases, the armature current increases, and the IR drop in the armature increases. The voltage delivered to the terminals. 12-135. A. Field rheostat. Dash. Load. SN. Plus. Shunt circuit main circuit. B. Field coils arm to load. Figure 12-286. Shunt wound generator. Is the difference between the induced voltage and the voltage drop. Therefore, there is a decrease in terminal voltage. This decrease in voltage causes a decrease in field strength, because the current in the field coils decreases in proportion to the decrease in terminal voltage. With a weaker field, the voltage is further decreased. When the load decreases, the output voltage increases accordingly, and a larger current flows in the windings. This action is cumulative, so the output voltage continues to rise to a point called field saturation, after which there is no further increase in output voltage. The terminal voltage of a shunt generator can be controlled by means of a rheostat inserted in series with the field windings. Figure 12-286A. As the resistance is increased, the field current is reduced. Consequently, the generated voltage is reduced also. For a given setting of the field rheostat, the terminal voltage at the armature brushes is approximately equal to the generated voltage, minus the IR drop produced by the load current in the armature. Thus, the voltage at the terminals of the generator drops as the load is applied. Certain voltage-sensitive devices are available that automatically adjust the field rheostat to compensate for variations in load. When these devices are used, the terminal voltage remains essentially constant. Compound wound DC generators. A compound wound generator combines a series winding and a shunt winding in such a way that the characteristics of each are used to advantage. The series field coils are made of a relatively small number of turns of large copper conductor, either circular or rectangular in cross-section, and are connected in series with the armature circuit. These coils are mounted on the same poles on which the shunt field coils are mounted and, therefore, contribute a magnetomotive force which influences the main field flux of the generator. A diagrammatic and a schematic illustration of a compound wound generator is shown in figure 12-287A and B. If the ampere turns of the series field act in the same direction as those of the shunt field, the combined magnetomotive force is equal to the sum of the series and shunt field components. Load is added to a compound generator in the same manner in which load is added to a shunt generator, by increasing the number of parallel paths across the generator terminals. Thus, the decrease in total load resistance with added load is accompanied by an increase in armature circuit and series field circuit current. The effect of the additive series field is that of increased field flux with increased load. The extent of the increased field flux depends on the degree of saturation of the field as determined by the shunt field current. Thus, the terminal voltage of the generator may increase or decrease with load, depending on the influence of the series field coils. This A-SN load plus B series field coil, shunt field coil to load arm compound wound. Figure 12-287 compound wound generator 12-136. Influence is referred to as the degree of compounding. A flat compound generator is one in which the no-load and full-load voltages have the same value, whereas an under-compound generator has a full-load voltage less than the no-load value, and an over-compound generator has a full-load voltage which is higher than the no-load value. Changes in terminal voltage with increasing load depend upon the degree of compounding. If the series field aids the shunt field, the generator is said to be cumulative compounded. If the series field opposes the shunt field, the machine is said to be differentially compounded or is called a differential generator. Compound generators are usually designed to be overcompounded. This feature permits varied degrees of compounding by connecting a variable shunt across the series field. Such a shunt is sometimes called a diverter. Compound generators are used where voltage regulation is of prime importance. Differential generators have somewhat the same characteristics as series generators in that they are essentially constant current generators. However, they generate rated voltage at no load, the voltage dropping materially as the load current increases. Constant current generators are ideally suited as power sources for electric arc welders, and are used almost universally in electric arc welding. If the shunt field of a compound generator is connected across both the armature and the series field, it is known as a long shunt connection, but if the shunt field is connected across the armature alone, it is called a short shunt connection. These connections produce essentially the same generator characteristics. A summary of the characteristics of the various types of generators discussed is shown in Figure 12-288. Generator ratings. A generator is rated in power output, since a generator is designed to operate at a specified voltage. The rating usually is given as the number of amperes the generator can safely supply at its rated voltage. Generator rating and performance data are stamped on the nameplate attached to the generator. When replacing a generator, it is important to choose one of the proper rating. The rotation of generators is termed either clockwise or counterclockwise, as viewed from the driven end. Usually, the direction of rotation is stamped on the data plate. If no direction is stamped on the plate, the rotation may be marked by an arrow on the cover plate of the brush housing. It is important that a generator with the correct direction of rotation be used. Otherwise, the voltage is reversed. The speed of an aircraft engine varies from idle RPM to takeoff RPM. However, during the major portion of a flight, it is at a constant cruising speed. The generator drive is usually geared to revolve the generator between 1 1/8 and 1 1/2 times the engine crankshaft speed. Most aircraft generators have a speed at which they begin to produce their normal voltage, termed coming-in speed. It is usually about 1,500 RPM. Generator terminals. On most large 24-volt generators, electrical connections are made to terminals marked B and D. The positive armature lead in the generator connects to the B terminal. The negative armature lead connects to the E terminal. The positive end of the shunt field winding connects to terminal A, and the opposite end connects to the negative terminal brush. Terminal receives current from the negative generator brush through the shunt field winding. This current passes through the voltage regulator and back to the armature. Output voltage 100%. Cumulative compounding. Shunt. Differential compounding. EC through the positive brush. Load current, which leaves the armature through the negative brushes, comes out of the E lead and passes through the load before returning to the armature through the positive brushes. Connection. Series connection. 0. Output current or load 100%. DC generator maintenance. Inspection. The following information about the inspection and maintenance of DC generator systems is general in nature because of the large number of differing aircraft generator systems. These procedures are for familiarization only. Always follow the applicable manufacturer's instructions for a given generator system. Figure 12-288. Generator characteristics. 12-137. In general, the inspection of the generator installed in the aircraft should include the following items. 1. Security of generator mounting. 2. Condition of electrical connections. 3. Dirt and oil in the generator. If oil is present, check engine oil seal. Blow out dirt with compressed air. 4. Condition of generator brushes. 5. Generator operation. 6. Voltage regulator operation. condition of generator brushes. Sparking of brushes quickly reduces the effective brush area in contact with the commutator bars. The degree of such sparking should be determined. Excessive wear warrants a detailed inspection. The following information pertains to brush seating, brush pressure, high mica condition, and brush wear. Manufacturers usually recommend the following procedures to seat brushes that do not make good contact with slip rings or commutators. Lift the brush sufficiently to permit the insertion of a strip of No. 000 or finer sandpaper under the brush. Rough side out. Figure 12-289. Pull the sandpaper in the direction of armature rotation, being careful to keep the ends of the unseated brush 1/32 to 1/16 000 sandpaper, sand side next to brush. Properly seated brush. Figure 12-289. Seating brushes with sandpaper. Sandpaper as close to the slip ring or commutator surface as possible in order to avoid rounding the edges of the brush. When pulling the sandpaper back to the starting point, raise the brush so it does not ride on the sandpaper. Sand the brush only in the direction of rotation. After the generator has run for a short period, brushes should be inspected to make sure that pieces of sand have not become embedded in the brush and are collecting copper. Under no circumstances should emery cloth or similar abrasives be used for seating brushes or smoothing commutators, since they contain conductive materials that cause arching between brushes and commutator bars. Excessive pressure causes rapid wear of brushes. Too little pressure, however, allows bouncing of the brushes, resulting in burned and pitted surfaces. A carbon, graphite, or light metallized brush should exert a pressure of 1 1/2 to 2 1/2 psi on the commutator. The pressure recommended by the manufacturer should be checked by the use of a spring scale graduated in ounces. Brush spring tension is usually adjusted between 32 to 36 ounces. However, the tension may differ slightly for each specific generator. When a spring scale is used, the measurement of the pressure that a brush exerts on the commutator is read directly on the scale. The scale is applied at the point of contact between the spring arm and the top of the brush, with the brush installed in the guide. The scale is drawn up until the arm just lifts off the brush surface. At this instant, the force on the scale should be read. Flexible low-resistance pigtails are provided on most heavy current-carrying brushes, and their connections should be securely made and checked at frequent intervals. The pigtail should never be permitted to alter or restrict the free motion of the brush. The purpose of the pigtail is to conduct the current, rather than subjecting the brush spring to currents that would alter its spring action by overheating. The pigtails also eliminate any possible sparking to the brush guides caused by the movement of the brushes within the holder, thus minimizing side wear of the brush. Carbon dust resulting from brush sanding should be thoroughly cleaned from all parts of the generators after a sanding operation. Such carbon dust has been the cause of several serious fires, as well as costly damage to the generator. 12-138. Operation over extended periods of time often results in the mica insulation between commutator bars protruding above the surface of the bars. This condition is called high mica and interferes with the contact of the brushes to the commutator. Whenever this condition exists, or if the armature has been turned on a lathe, carefully undercut the mica insulation to a depth equal to the width of the mica, or approximately 1.20 inch. Each brush should be a specified length to work properly. If a brush is too short, the contact it makes with the commutator will be faulty, which can also reduce the spring force holding the brush in place. Most manufacturers specify the amount of wear permissible from a new brush length. When a brush has worn to the minimum length permissible, it must be replaced. Some special generator brushes should not be replaced because of a slight grooving on the face of the brush. These grooves are normal and will appear in AC and DC generator brushes which are installed in some models of aircraft generators. These brushes have two cores made of a harder material with a higher expansion rate than the material used in the main body of the brush. Usually, the main body of the brush face rides on the commutator. However, at certain temperatures, the cores extend and wear through any film on the commutator. DC motors. Most devices in an airplane, from the starter, figure 12-290, to the automatic pilot, depend upon mechanical energy furnished by DC motors. A DC motor is a rotating machine, which transforms DC energy into mechanical energy. It consists of two principal parts, a field assembly and an armature assembly. The armature is the rotating part in which current-carrying wires are acted upon by the magnetic field. Whenever a current-carrying wire is placed in the field of a magnet, a force acts on the wire. The force is not one of figure 12-290. DC series starter motor. Attraction or repulsion. However, it is at right angles to the wire, and also at right angles to the magnetic field set up by the magnet. The action of the force upon a current-carrying wire placed in a magnetic field is shown in figure 12-291. A wire is located between two permanent magnets. The lines of force in the magnetic field are from the North Pole to the South Pole. When no current flows, no force is exerted on the wire. But when current flows through the wire, a magnetic field is set up about it. Figure 12-291. The direction of the field depends on the direction of current flow. Current in one direction creates a clockwise field about the wire, and current in the other direction, a counterclockwise field. Since the current-carrying wire produces a magnetic field, a reaction occurs between the field about the wire and the magnetic field between the magnets. When the current flows in a direction, to create a counterclockwise magnetic field about the wire, this field and the field between the magnets add or reinforce at the bottom of the wire, because the lines of force are in the same direction. At the top of the wire, they subtract or neutralize, since the lines of force in the two fields are opposite in direction. Thus, the resulting field at the bottom is strong, and the one at the top is weak. Consequently, the wire is pushed upward. Figure 12-291c. The wire is always pushed away from the side where the field is strongest. A BC. Wire without current located in a magnetic field. Figure 12-291. Force on a current-carrying wire. Wire with current and accompanying field. Resultant field and direction of force on wire. 12-139. If current flow through the wire were reversed in direction, the two fields would add at the top and subtract at the bottom. Since a wire is always pushed away from the strong field, the wire would be pushed down. Force between parallel conductors. Two wires carrying current in the vicinity of one another exert a force on each other because of their magnetic fields. An end view of two conductors is shown in Figure 12-292. In Figure 12-292a, electron flow in both conductors is toward the reader, and the magnetic fields are clockwise around the conductors. Between the wires, the fields cancel because the directions of the two fields oppose each other. The wires are forced in the direction of the weaker field, toward each other. This force is one of attraction. In Figure 12-292b, the electron flow in the two wires is in opposite directions. The magnetic fields are, therefore, clockwise in one and counterclockwise in the other, as shown. The fields reinforce each other between the wires, and the wires are forced in the direction of the weaker field, away from each other. This force is one of repulsion. To summarize, conductors carrying current in the same direction tend to be drawn together. Conductors carrying current in opposite directions tend to be repelled from each other. Developing torque. If a coil in which current is flowing is placed in a magnetic field, a force is produced which causes the coil to rotate. In the coil shown in Figure 12-293, current flows inward on side A and outward on side B. The magnetic field about B is clockwise and that about A counterclockwise. As previously explained, a force develops which pushes side B downward. At the same time, the field of the magnets and the field about A, in which the current is inward, adds at the bottom and subtracts at the top. Therefore, A moves upward. The coil rotates until its plane is perpendicular to the magnetic lines between the north and south poles of the magnet, as indicated in Figure 12-293 by the white coil at right angles to the black coil. The tendency of a force to produce rotation is called torque. When the steering wheel of a car is turned, torque is applied. The engine of an airplane gives torque to the propeller. Torque is developed also by the reacting magnetic fields about the current-carrying coil just described. This is the torque, which turns the coil. The right-hand motor rule can be used to determine the direction a current-carrying wire moves in a magnetic field. As illustrated in Figure 12-294. If the index finger of the magnetic field torque, direction of current, A B, and S, A. Figure 12-293. Developing a torque, motion, plus magnetic flux, current, B. Figure 12-294. Right-hand motor rule. Figure 12-292. Field surrounding parallel conductors. 12-140. Right hand is pointed in the direction of the magnetic field, and the second finger in the direction of current flow. The thumb indicates the direction the current-carrying wire moves. The amount of torque developed in a coil depends upon several factors: the strength of the magnetic field, the number of turns in the coil, and the position of the coil in the field. Magnets are made of special steel that produces a strong field. Since there is torque acting on each turn, the greater the number of turns on the coil, the greater the torque. In a coil carrying a steady current located in a uniform magnetic field, the torque varies at successive positions of rotation. Figure 12-295. When the plane of the coil is parallel to the lines of force, the torque is 0. When its plane cuts the lines of force at right angles, the torque is 100%. At intermediate positions, the torque ranges between 0 and 100%. Basic DC motor. a coil of wire through which the current flows rotates when placed in a magnetic field. This is the technical basis governing the construction of a DC motor. Figure 12-296. However, if the connecting wires from the battery were permanently fastened to the terminals of the coil and there was a flow of current, the coil would rotate only until it lined itself up with the magnetic field. Then, it would stop, because the torque at that point would be zero. A motor, of course, must continue rotating. It is therefore necessary to design a device that reverses the current in the coil just at the time the coil becomes parallel to the lines of force. This creates torque again and causes the coil to rotate. If the current reversing device is set up to reverse the current each time the coil is about to stop, the coil can be made to continue rotating as long as desired. One method of doing this is to connect the circuit so that, as the coil rotates, each contact slides off the terminal to which it connects and slides onto the terminal of opposite polarity. In other words, the coil contacts switch terminals continuously as the coil rotates, preserving the torque and keeping the coil rotating. In figure 12-296, the coil terminal segments A. Torque, NS. Brush. A B. No torque, B. NS. A. C. Torque, NS. BA. D. No torque. 0 torque. 100% 71%. 0 degrees 90 degrees. S. A. NS. N. 45 degrees. B. Figure 12-295. Torque on a coil at various angles of rotation. Figure 12-296. Basic DC motor operation. 12-141. Are labeled A and B. As the coil rotates, the segments slide onto and past the fixed terminals or brushes. With this arrangement, the direction of current in the side of the coil next to the north-seeking pole flows toward the reader, and the force acting on that side of the coil turns it downward. The part of the motor that changes the current from one wire to another is called the commutator. Position A. When the coil is positioned as shown in figure 12-296A, current flows from the negative terminal of the battery to the negative brush to segment B of the commutator, through the loop to segment A of the commutator, to the positive plus brush, and then back to the positive terminal of the battery. By using the right-hand motor rule, it is seen that the coil rotates counterclockwise. The torque at this position of the coil is maximum, since the greatest number of lines of force is being cut by the coil. Position B. When the coil has rotated 90 degrees to the position shown in figure 12-296B, segments A and B of the commutator no longer make contact with the battery circuit and no current can flow through the coil. At this position, the torque has reached a minimum value, since a minimum number of lines of force are being cut. However, the momentum of the coil carries it beyond this position until the segments again make contact with the brushes, and current again enters the coil. This time, though, it enters through segment A and leaves through segment B. However, since the positions of segments A and B have also been reversed, the effect of the current is as before. The torque acts in the same direction, and the coil continues its counterclockwise rotation. Position C. On passing through the position shown in figure 12-296C, the torque again reaches maximum. Position D. Continued rotation carries the coil again to a position of minimum torque as in figure 12-296D. At this position, the brushes no longer carry current, but once more the momentum rotates the coil to the point where current enters through segment B and leaves through A. Further rotation brings the coil to the starting point and, thus, one revolution is completed. The switching of the coil terminals from the positive to the negative brushes occurs twice per revolution of the coil. The torque in a motor containing only a single coil is neither continuous nor very effective, for there are two positions where there is actually no torque at all. To overcome this, a practical DC motor contains a large number of coils wound on the armature. These coils are so spaced that, for any position of the armature, there are coils near the poles of the magnet. This makes the torque both continuous and strong. The commutator, likewise, contains a large number of segments instead of only two. The armature in a practical motor is not placed between the poles of a permanent magnet, but between those of an electromagnet. Since a much stronger magnetic field can be furnished, the core is usually made of a mild or annealed steel, which can be magnetized strongly by induction. The current magnetizing the electromagnet is from the same source that supplies the current to the armature. DC motor construction. The major parts in a practical motor are the armature assembly, the field assembly, the brush assembly, and the end frame. Figure 12-297. Armature assembly. The armature assembly contains a laminated, soft iron core, coils, and a commutator, all mounted on a rotatable steel shaft. Laminations made of stacks of soft iron, insulated from each other, form the armature core. Solid iron is not used, since a solid iron core revolving in the magnetic field would heat and use energy needlessly. The armature windings are insulated copper wire, which are inserted in slots insulated with fiber paper, fish paper, to protect the windings. The ends of the windings are connected to the commutator segments. Wedges or steel bands hold the windings in place to prevent them from flying out of the slots. When the armature is rotating at high speeds, the commutator consists of a large number of copper segments insulated from each other, and the armature shaft by pieces of mica. Insulated wedge rings hold the segments in place. Field assembly. The field assembly consists of the field frame, the pole pieces, and the field coils. The field frame is located along the inner wall of the motor housing. It contains laminated, soft steel pole pieces on which the field coils are wound. A coil, consisting of several turns of insulated wire, fits over each pole piece and, together with the pole, constitutes a field pole. Some motors have as few as 2 poles, others as many as 8. Brush assembly. The brush assembly consists of the brushes and their holders. The brushes are usually small blocks of graphitic carbon, since this material has a long service life, and also causes minimum wear to the commutator. The holders permit some playing the brushes, so they can follow any irregularities in the surface. 12-142. End frame commutator. Field coils bearing. Armature. Cover brush rigging. Figure 12-297. Cutaway view of practical DC motor of the commutator and make good contact. Springs hold the brushes firmly against the commutator. Figure 12-298. End frame. The end frame is the part of the motor opposite the commutator. Usually, the end frame is designed so that it can be connected to the unit to be driven. The bearing for the drive end is also located in the end frame. Sometimes the end frame is made a part of the unit driven by the motor. When this is done, the bearing on the drive end may be located in any one of a number of places. Tube-type brush. Box-type brush. Figure 12-298. Commutator and brushes. 12-143. Types of DC motors. There are 3 basic types of DC motors: series motors, shunt motors, and compound motors. They differ largely in the method in which their field and armature coils are connected. Series DC motor. In the series motor, the field windings, consisting of a relatively few turns of heavy wire, are connected in series with the armature winding. Both a diagrammatic and a schematic illustration of a series motor are shown in figure 12-299. The same current flowing through the field winding also flows through the armature winding. Any increase in current, therefore, strengthens the magnetism of both the field and the armature. Because of the low resistance in the windings, the series motor is able to draw large current in starting. This starting current, in passing through both the field and armature windings, produces a high starting torque, which is the series motor's principal advantage. The speed of a series motor is dependent upon the load. Any change in load is accompanied by a substantial change in load and at low speed with a heavy load. If the load is removed entirely, the motor may operate at such a high speed that the armature falls apart. If high starting torque is needed under heavy load conditions, series motors have many applications. Series motors are often used in aircraft as engine starters, and for raising and lowering landing gears, cowl flaps, and wing flaps. Shunt DC motor. In the shunt motor, the field winding is connected in parallel, or in shunt with the armature winding. Figure 12-300. The resistance in the field winding is high. Since the field winding is connected directly across the power supply, the current through the field is constant. The field current does not vary with motor speed, as in the series motor, and, therefore, the torque of the shunt motor varies only with the current through the armature. The torque developed at starting is less than that developed by a series motor of equal size. The speed of the shunt motor varies very little with changes in load. When all load is removed, it assumes a speed slightly higher than the loaded speed. This motor is particularly suitable for use when constant speed is desired and when high starting torque is not needed. Speed. A series motor runs at high speed when it has a light wire shunt field. Commutator armature. Armature. Commutator. A. Diagrammatic. A. Diagrammatic. Shunt field. B. Schematic. B. Schematic. Figure 12-299. Series motor. Figure 12-300. Shunt motor. 12-144. Compound DC motor. The compound motor is a combination of the series and shunt motors. There are 2 windings in the field: a shunt winding and a series winding. Figure 12-301. The shunt winding is composed of many turns of fine wire, and is connected in parallel with the armature winding. The series winding consists of a few turns of large wire, and is connected in series with the armature winding. The starting torque is higher than in the shunt motor, but lower than in the series motor. Variation of speed with load is less than in a series wound motor, but greater than in a shunt motor. The compound motor is used whenever the combined characteristics of the series and shunt motors are desired. Like the compound generator, the compound motor has both series and shunt field windings. The series winding may either aid the shunt wind, cumulative compound, or oppose the shunt winding, differential compound. The starting and load characteristics of the cumulative compound motor are somewhere between those of the series and those of the shunt motor. Because of the series field, the cumulative compound motor has a higher starting torque than a shunt motor. Cumulative compound motors are used in driving machines, which are subject to sudden changes in load. They are also used where a high starting torque is desired, but a series motor cannot be used easily. In the differential compound motor, an increase in load creates an increase in current and a decrease in total flux in this type of motor. These two tend to offset each other, and the result is a practically constant speed. However, since an increase in load tends to decrease the field strength, the speed characteristic becomes unstable. Rarely is this type of motor used in aircraft systems. A graph of the variation in speed with changes of load of the various types of DC motors is shown in figure 12-302. 100% speed of rotation. Differential. Compounding. Shunt. Connection cumulative compounding. Series connection. Zero output power, or load 100%. Plus. Series field. Shunt field. M. Dash. Figure 12-301. Compound motor. Figure 12-302. Load characteristics of DC motors. Counter-electromotive force EMF. The armature resistance of a small 28-volt DC motor is extremely low, about 0.1 ohm. When the armature is connected across the 28-volt source, current through the armature is apparently E28 = 280 amperes or 0.1. This high value of current flow is not only impracticable, but also unreasonable, especially when the current drain, during normal operation of a motor, is found to be about 4 amperes. This is because the current through a motor armature during operation is determined by more factors than ohmic resistance. When the armature in a motor rotates in a magnetic field, a voltage is induced in its windings. This voltage is called the back or counter EMF, and is opposite in direction to the voltage applied to the motor from the external source. Counter EMF opposes the current, which causes the armature to rotate. The current flowing through the armature, therefore, decreases as the counter EMF increases. The faster the armature rotates, the greater the counter EMF. For this reason, a motor connected to a battery may draw fairly high current on starting, but as the armature speed increases, the current flowing through the armature decreases. At rated speed, the counter EMF may be only a few volts less than the battery voltage. Then, if the load on the motor is increased, the motor slows down, less counter EMF is generated, and the current drawn from the external source increases. In a shunt motor, the counter EMF affects only the current in the armature, since the field is connected in parallel across the power source. As the motor slows down and the counter EMF decreases, more current flows through the armature, but the magnetism in the 12-145 field is unchanged. When the series motor slows down, the counter EMF decreases and more current flows through the field and the armature, thereby strengthening their magnetic fields. Because of these characteristics, it is more difficult to stall a series motor than a shunt motor. Types of duty. Electric motors are called upon to operate under various conditions. Some motors are used for intermittent operation. Others operate continuously. Motors built for intermittent duty can be operated for short periods only and, then, must be allowed to cool before being operated again. If such a motor is operated for long periods under full load, the motor becomes overheated. Motors built for continuous duty may be operated at rated power for long periods. Reversing motor direction. By reversing the direction of current flow in either the armature or the field windings, the direction of a motor's rotation may be reversed. This reverses the magnetism of either the armature or the magnetic field in which the armature rotates. If the wires connecting the motor to an external source are interchanged, the direction of rotation is not reversed, since changing these wires reverses the magnetism of both field and armature, and leaves the torque in the same direction as before. Current flows through the lower field winding, creating a north pole at the lower field winding, and at the lower pole piece, and a south pole at the upper pole piece. When the switch is placed in the upper position, current flows through the upper field winding, the magnetism of the field is reversed, and the armature rotates in the opposite direction. Some split field motors are built with two separate field windings wound on alternate poles. The armature in such a motor A 4-pole reversible motor rotates in one direction when current flows through the windings of one set of opposite pole pieces, and in the opposite direction when current flows through the other set of windings. Another method of direction reversal, called the switch method, employs a double pole, double through switch which changes the direction of current flow in either the armature or the field. In the illustration of the switch method shown in figure 12-304, current direction may be reversed through the field, but not through the armature. When the switch is thrown to the up position, current flows through the field winding to establish a north pole at the right side of the motor, and a south pole at the left side of the motor. When the switch is thrown to the down position, this polarity is reversed and the armature rotates in the opposite direction. One method for reversing direction of rotation employs two field windings wound in opposite directions on the same pole. This type of motor is called a split field motor. Figure 12-303, the single pole double through a switch makes it possible to direct current through either of the two windings. When the switch is placed in the lower position, B, up, A, double pole, double through a switch down. Figure 12-304, switch method of reversing motor direction. Figure 12-303, split field series motor. 12-146. Motor speed. Motor speed can be controlled by varying the current in the field windings. When the amount of current flowing through the field windings is increased, the field strength increases, but the motor slows down since a greater amount of counter-EMF is generated in the armature windings. When the field current is decreased, the field strength decreases, and the motor speeds up because the counter-EMF is reduced. A motor in which speed can be controlled is called a variable speed motor. It may be either a shunt or series motor. In the shunt motor, speed is controlled by a rheostat in series with the field windings. Figure 12-305. The speed depends on the amount of current that flows through the rheostat to the field windings. To increase the motor speed, the resistance in the rheostat is increased, which decreases the field current. As a result, there is a decrease in the strength of the magnetic field and in the counter-EMF. This momentarily increases the armature current and the torque. The motor then automatically speeds up until the counter-EMF increases, and causes the armature current to decrease to its former value. When this occurs, the motor operates at a higher fixed speed than before. To decrease the motor speed, the resistance of the rheostat is decreased. More current flows through the field windings, and increases the strength of the field. Then, the counter-EMF increases momentarily and decreases the armature current. As a result, the torque decreases and the motor slows down. Frame, pole, shunt lead, commutator, armature, rheostat, until the counter-EMF decreases to its former value. Then the motor operates at a lower fixed speed than before. In the series motor, the rheostat speed control is connected either in parallel, or in series with the motor field, or in parallel with the armature. When the rheostat is set for maximum resistance, the motor speed is increased in the parallel armature connection by a decrease in current. When the rheostat resistance is maximum in the series connection, motor speed is reduced by a reduction in voltage across the motor. For above normal speed operation, the rheostat is in parallel with the series field. Part of the series field current is bypassed and the motor speeds up. Figure 12-306. Energy losses in DC motors. Losses occur when electrical energy is converted to mechanical energy in the motor, or mechanical energy is converted to electrical energy in the generator. For the machine to be efficient, these losses must be kept to a minimum. Some losses are electrical, others are mechanical. Electrical losses are classified as copper losses and iron losses. Mechanical losses occur in overcoming the friction of various parts of the machine. Copper losses occur when electrons are forced through the copper windings of the armature and the field. These losses are proportional to the square of the current. They are sometimes called I2R losses, since they are due to the power dissipated in the form of heat in the resistance of the field and armature windings. Iron losses are subdivided in hysteresis and eddy current losses. Hysteresis losses are caused by the armature revolving in an alternating magnetic field. It, therefore, becomes magnetized first in one direction and then in the other. The residual magnetism of the iron or steel of which the armature is made causes these losses. Since the field magnets are always magnetized in one direction, DC field, they have no hysteresis losses. Eddy current losses occur because the iron core of the armature is a conductor revolving in a magnetic field. This sets up an EMF across portions of the core, causing currents to flow within the core. These currents heat the core and, if they become excessive, may damage the windings. As far as the output is concerned, the power consumed by eddy currents is a loss. To reduce eddy currents to a minimum, a laminated core usually is used. A laminated core is made of thin sheets of iron electrically insulated from each other. The insulation between laminations reduces eddy currents because it is transverse to the direction in which these currents tend to flow. However, it has no effect on the magnetic circuit. The Figure 12-305 Shunt motor with variable speed control. 12-147 plus slow fast plus series filed rheostat slow fast slow m dash below normal speed above normal speed. Figure 12-306 Controlling the speed of a series DC motor. Thinner the laminations, the more effectively this method reduces eddy current losses. Inspection and maintenance of DC motors. Use the following procedures to make inspection and maintenance checks. 1. Check the operation of the unit driven by the motor in accordance with the instructions covering the specific installation. 2. Check all wiring, connections, terminals, fuses, and switches for general condition and security. 3. Keep motors clean and mounting bolts tight. 4. Check brushes for condition, length, and spring tension. Minimum brush lengths, correct spring tension, and procedures for replacing brushes are given in the applicable manufacturer's instructions. 5. Inspect commutator for cleanness, pitting, scoring, roughness, corrosion, or burning. Check for high mica. If the copper wears down below the mica insulates the brushes from the commutator. Clean dirty commutators with a cloth moistened with the recommended cleaning solvent. Polish rough or corroded commutators with fine sandpaper, 000, or finer, and blow out with compressed air. Never use emery paper, since it contains metallic particles that may cause shorts. Replace the motor if the commutator is burned, badly pitted, grooved, or worn, to the extent that the mica insulation is flush with the commutator surface. 6. Inspect all exposed wiring for evidence of overheating. Replace the motor if the insulation on leads or windings is burned, cracked, or brittle. 7. Lubricate only if called for by the manufacturer's instructions covering the motor. Most motors used in today's airplanes require no lubrication between overhauls. 8. Adjust and lubricate the gearbox, or unit which the motor drives, in accordance with the applicable manufacturer's instructions covering the unit. When trouble develops in a DC motor system, check first to determine the source of the trouble. Replace the motor only when the trouble is due to a defect in the motor itself. In most cases, the failure of a motor to operate is caused by a defect in the external electrical circuit or by mechanical failure in the mechanism driven by the motor. Check the external electrical circuit for loose or dirty connections, and for improper connection of wiring. Look for open circuits, grounds, and shorts by following the applicable manufacturer's circuit testing procedure. If the fuse is not blown, failure of the motor to operate is usually due to an open circuit. A blown fuse usually indicates an accidental ground or short circuit. A low battery usually causes the chattering of the relay switch, which controls the 12-148 motor. When the battery is low, the open circuit voltage of the battery is sufficient to close the relay, but with the heavy current draw of the motor, the voltage drops below the level required to hold the relay closed. When the relay opens, the voltage in the battery increases enough to close the relay again. This cycle repeats and causes chattering, which is very harmful to the relay switch due to the heavy current causing an arc which burns the contacts. Check the unit driven by the motor for failure of the unit or drive mechanism. If the motor has failed as a result of a failure in the driven unit, the fault must be corrected before installing a new motor. If it has been determined that the fault is in the motor itself, by checking for correct voltage at the motor terminals, and for failure of the driven unit, inspect the commutator and brushes. A dirty commutator, or defective or binding brushes may result in poor contact between brushes and commutator. Clean the commutator, brushes, and brush holders with a cloth moistened with the recommended cleaning solvent. If brushes are damaged or worn to the specified minimum length, install new brushes in accordance with the applicable manufacturer's instructions covering the motor. If the motor still fails to operate, replace it with a serviceable motor. AC motors. Because of their advantages, many types of aircraft motors are designed to operate on alternating current. In general, AC motors are less expensive than comparable DC motors. In many instances, AC motors do not use brushes, and commutators, so sparking at the brushes is avoided. AC motors are reliable and require little maintenance. They are also well suited for constant speed applications, and certain types are manufactured that have, within limits, variable speed characteristics. Alternating current motors are designed to operate on polyphase or single-phase lines, and at several voltage ratings. The speed of rotation of an AC motor depends upon the number of poles and the frequency of the electrical source of power. 120 times frequency RPM equals number of poles. Since airplane electrical systems typically operate at 400 cycles, an electric motor at this frequency operates at about 7 times the speed of a 60-cycle commercial motor with the same number of poles. Because of this high speed of rotation, 400-cycle AC motors are suitable for operating small, high-speed rotors. Through reduction gears, in lifting and moving heavy loads, such as the wing flaps, the retractable landing gear, and the starting of engines. The 400-cycle induction type motor operates at speeds ranging from 6,000 RPM to 24,000 RPM. Alternating current motors are rated in horsepower output, operating voltage, full load current, speed, number of phases, and frequency. Whether the motors operate continuously or intermittently, for short intervals, is also considered in the rating. Types of AC motors. There are 2 general types of AC motors used in aircraft systems: induction motors and synchronous motors. Either type may be single-phase, 2-phase, or 3-phase. 3-phase induction motors are used where large amounts of power are required. They operate such devices as starters, flaps, landing gears, and hydraulic pumps. Single-phase induction motors are used to operate devices such as surface locks, intercooler shutters, and oil shutoff valves in which the power requirement is low. 3-phase synchronous motors operate at constant synchronous speeds, and are commonly used to operate flux gate compasses and propeller synchronizer systems. Single-phase synchronous motors are common sources of power to operate electric clocks and other small precision equipment. They require some auxiliary method to bring them up to synchronous speeds. That is, to start them. Usually the starting winding consists of an auxiliary stator winding. 3-phase induction motor. The 3-phase AC induction motor is also called a squirrel cage motor. Both single-phase and 3-phase motors operate on the principle of a rotating magnetic field. A horseshoe magnet held over a compass needle is a simple illustration of the principle of the rotating field. The needle takes a position parallel to the magnetic flux passing between the 2 poles of the magnet. If the magnet is rotated, the compass needle follows. A rotating magnetic field can be produced by a 2- or 3-phase current flowing through 2 or more groups of coils wound on inwardly projecting poles of an iron frame. The coils on each group of poles are wound alternately in opposite directions to produce opposite polarity, and each group is connected to a separate phase of voltage. The operating principle depends on a revolving, or rotating, magnetic field to produce torque. The key to understanding the induction motor is a thorough understanding of the rotating magnetic field. Rotating magnetic field. The field structure shown in Figure 12-307A has poles whose windings are energized by 3 AC voltages.